In statistics, the Pearson product moment correlation coefficient is a measure of the linear correlation between two variables x and y, giving a value between +1 and -1 inclusive, where 1 is total positive correlation, 0 is no correlation, and -1 is total negative correlation. It is widely used in the sciences as a measure of the degree of linear dependence between two variables. It was developed by Carl Pearson from a related idea introduced by Francis Galton in the 1880s. Early work on the distribution of the sample correlation coefficient was carried out by Anil Kumar Gain and R. A. Fisher from the University of Cambridge. Definition: Pearson's correlation coefficient is the covariance of the two variables divided by the product of their standard deviations. The form of the definition involves a product moment, that is, the mean of the product of the mean-adjusted random variables, hence the modifier product moment in the name. For a population, Pearson's correlation coefficient when applied to a population is commonly represented by the Greek letter ρ and may be referred to as the population correlation coefficient or the population Pearson correlation coefficient. The formula for ρ is where is the covariance is the standard deviation of. The formula for ρ can be expressed in terms of mean and expectation. Since then the formula for ρ can also be written as where, and are defined as above, is the mean of, is the expectation. The formula for ρ can be expressed in terms of uncentered moments. Since then the formula for ρ can also be written as for a sample. Pearson's correlation coefficient when applied to a sample is commonly represented by the letter r and may be referred to as the sample correlation coefficient or the sample Pearson correlation coefficient. We can obtain a formula for r by substituting estimates of the covariances and variances based on a sample into the formula above. So if we have one dataset x1, xn, containing n values and another dataset y1, yn, containing n values, then that formula for r is where are defined as above, and analogously for rearranging gives us this formula for r, where are defined as above. This formula suggests a convenient single-pass algorithm for calculating sample correlations, but, depending on the numbers involved, it can sometimes be numerically unstable. Rearranging again gives us this formula for r, where are defined as above. An equivalent expression gives the formula for r as the mean of the products of the standard scores as follows: where are defined as above, and I defined below, is the standard score. Alternative formulae for r are also available. One can use the following formula for r, where are defined as above and analogously for psi. Mathematical properties. The absolute values of both the sample and population Pearson correlation coefficients are less than or equal to 1. Correlations equal to 1 or -1 correspond to data points lying exactly on a line, or to a bivariate distribution entirely supported on a line. The Pearson correlation coefficient is symmetric. Core equals core. A key mathematical property of the Pearson correlation coefficient is that it is invariant to separate changes in location and scale in the two variables. That is, we may transform x to a plus bx and transform y to c plus dy, where a, b, c, and d are constants with b, d0, without changing the correlation coefficient. Note that more general linear transformations do change the correlation. See a later section for an application of this. Interpretation. The correlation coefficient ranges from -1 to 1. A value of 1 implies that a linear equation describes the relationship between x and y perfectly, with all data points lying on a line for which y increases as x increases. A value of -1 implies that all data points lie on a line for which y decreases as x increases. A value of 0 implies that there is no linear correlation between the variables. More generally, note that is positive if and only if xi and yi lie on the same side of their respective means. Thus the correlation coefficient is positive if xi and yi tend to be simultaneously greater than, or simultaneously less than, their respective means. The correlation coefficient is negative if xi and yi tend to lie on opposite sides of their respective means. Moreover, the stronger is either tendency, the larger is the absolute value of the correlation coefficient. Geometric interpretation for unscented data. It is possible to obtain a relation between correlation coefficient and the angle between both possible regression lines y equals gx and x equals gy. One can show that r equals sec tan. For scented data, the correlation coefficient can also be viewed as the cosine of the angle between the two vectors of samples in n-dimensional space. Both the unscented and scented correlation coefficients can be determined for a dataset. As an example, suppose 5 countries are found to have gross national products of $1, $2, $3, $5, and $8 billion, respectively. Suppose these same 5 countries are found to have 11%, 12%, 13%, 15%, and 18% poverty. Then let x and y be ordered 5-element vectors containing the above data, x equals and y equals. By the usual procedure for finding the angle between two vectors, the unscented correlation coefficient is. Note that the above data were deliberately chosen to be perfectly correlated. Y equals 0.10 plus 0.01x. The Pearson correlation coefficient must therefore be exactly 1. Centering the data equals 3.8 and y by e equals 0.138 yields x equals and y equals, from which as expected. Interpretation of the size of a correlation. Several authors have offered guidelines for the interpretation of a correlation coefficient. However, all such criteria are in some ways arbitrary and should not be observed too strictly. The interpretation of a correlation coefficient depends on the context and purposes. A correlation of 0.8 may be very low if one is verifying a physical law using high-quality instruments, but may be regarded as very high in the social sciences where there may be a greater contribution from complicating factors. Inference. Statistical inference based on Pearson's correlation coefficient often focuses on one of the following two aims. One aim is to test the null hypothesis that the true correlation coefficient ρ is equal to 0, based on the value of the sample correlation coefficient r. The other aim is to derive a confidence interval that, on repeated sampling, has a given probability of containing ρ. We discuss methods of achieving one or both of these aims below. Using a permutation test. Permutation tests provide a direct approach to performing hypothesis tests and constructing confidence intervals. A permutation test for Pearson's correlation coefficient involves the following two steps. Using the original paired data, randomly redefine the pairs to create a new data set, where the I are a permutation of the set 1, n. The permutation I is selected randomly, with equal probabilities placed on all n possible permutations. This is equivalent to drawing the I randomly, without replacement, from the set 1, n. A closely related and equally justified approach is to separately draw the I and the I, with replacement, from 1, n. Construct a correlation coefficient R from the randomized data. To perform the permutation test, repeat steps a large number of times. The p-value for the permutation test is the proportion of the R values generated in step that are larger than the Pearson correlation coefficient that was calculated from the original data. Here, larger can mean either that the value is larger in magnitude, or larger in sign value, depending on whether a two-sided or one-sided test is desired. Using a bootstrap. The bootstrap can be used to construct confidence intervals for Pearson's correlation coefficient. In the non-parametric bootstrap, n pairs are resampled, with replacement, from the observed set of n pairs, and the correlation coefficient R is calculated based on the resampled data. This process is repeated a large number of times, and the empirical distribution of the resampled R values are used to approximate the sampling distribution of the statistic. A 95% confidence interval for ρ can be defined as the interval spanning from the 2/5 to the 97/5 percentile of the resampled R values. Testing using students' t-distribution for pairs from an uncorrelated bivariate normal distribution. The sampling distribution of a certain function of Pearson's correlation coefficient follows students' t-distribution with degrees of freedom n-2. Specifically, if the underlying variables have a bivariate normal distribution, the variable has a students' t-distribution in the null case. This also holds approximately even if the observed values are non-normal, provided sample sizes are not very small. For determining the critical values for R, the inverse of this transformation is also needed. Alternatively, large sample approaches can be used. Early work on the distribution of the sample correlation coefficient was carried out by Anil Kumar Gain and R. A. Fisher. Another early paper provides graphs and tables for general values of ρ for small sample sizes, and discusses computational approaches using the exact distribution for data that follows a bivariate normal distribution. The exact density function f for the sample correlation coefficient R of a normal bivariate is where is the gamma function, is the Gaussian hypergeometric function. In the special case when the exact density function f can be written as where is the beta function, which is one way of writing the density of a student's t-distribution, as above. Using the Fisher transformation in practice, confidence intervals and hypothesis tests relating to ρ are usually carried out using the Fisher transformation. If f is the Fisher transformation of R, and n is the sample size, then f approximately follows a normal distribution with an standard error. Thus, a z-score is under the null hypothesis of that, given the assumption that the sample pairs are independent and identically distributed and follow a bivariate normal distribution. Thus, an approximate p-value can be obtained from a normal probability table. For example, if z equals 2.2 is observed and a two-sided p-value is desired to test the null hypothesis that the p-value is 2 phi equals 0.028, where phi is the standard normal cumulative distribution function. To obtain a confidence interval for ρ, we first compute a confidence interval for f equals 0.30952. So the confidence interval on the transformed scale is 0.30952 plus or minus 1.96 square root 47, or, converting back to the correlation scale, yields Pearson's correlation and least squares regression analysis. The square of the sample correlation coefficient is typically denoted R2 and is a special case of the coefficient of determination. In this case, it estimates the fraction of the variance in Y that is explained by X in a simple linear regression. So if we have the observed dataset Y1, Yn, and the fitted dataset F1, Fn, and we denote the fitted dataset F1, Fn with Y1, Yn, then as a starting point the total variation in the year around their average value can be decomposed as follows, where the are the fitted values from the regression analysis. This can be rearranged to give the two sum answer above the fraction of variance in Y that is explained by X and that is unexplained by X. Next, we apply a property of least square regression models, that the sample covariance between n is 0. Thus, the sample correlation coefficient between the observed and fitted response values in the regression can be written thus, where is the proportion of variance in Y explained by a linear function of X. That equation can be written as where is the regression sum of squares, also called the explained sum of squares, is the total sum of squares. Sensitivity to the data distribution. Existence. The population Pearson correlation coefficient is defined in terms of moments, and therefore exists for any bivariate probability distribution for which the population covariance is defined and the marginal population variances are defined and are non-zero. Some probability distributions, such as the Cauchy distribution, have undefined variance, and hence ρ is not defined if x or y follows such a distribution. In some practical applications, such as those involving data suspected to follow a heavy-tailed distribution, this is an important consideration. However, the existence of the correlation coefficient is usually not a concern. For instance, if the range of the distribution is bounded, ρ is always defined. Sample size: if the sample size is moderate or large and the population is normal, then in the case of the bivariate normal distribution, the sample correlation coefficient is the maximum likelihood estimate of the population correlation coefficient, and is asymptotically unbiased and efficient, which roughly means that it is impossible to construct a more accurate estimate than the sample correlation coefficient. If the sample size is large and the population is not normal, then the sample correlation coefficient remains approximately unbiased, but may not be efficient. If the sample size is large, then sample correlation coefficient is a consistent estimator of the population correlation coefficient as long as the sample means, variances, and covariance are consistent. If the sample size is small, then the sample correlation coefficient R is not an unbiased estimate of ρ. The adjusted correlation coefficient must be used instead. See elsewhere in this article for the definition. Robustness: like many commonly used statistics, the sample statistic R is not robust, so its value can be misleading if outliers are present. Specifically, the PPMCC is neither distributionally robust nor outlier resistant. Inspection of the scatter plot between x and y will typically reveal a situation where lack of robustness might be an issue, and in such cases it may be advisable to use a robust measure of association. Note, however, that while most robust estimators of association measure statistical dependence in some way, they are generally not interpretable on the same scale as the Pearson correlation coefficient. Statistical inference for Pearson's correlation coefficient is sensitive to the data distribution. Exact tests and asymptotic tests based on the Fisher transformation can be applied if the data are approximately normally distributed, but may be misleading otherwise. In some situations, the Bootstrap can be applied to construct confidence intervals, and permutation tests can be applied to carry out hypothesis tests. These non-parametric approaches may give more meaningful results in some situations where bivariate normality does not hold. However, the standard versions of these approaches rely on exchangeability of the data, meaning that there is no ordering or grouping of the data pairs being analyzed that might affect the behavior of the correlation estimate. A stratified analysis is one way to either accommodate a lack of bivariate normality, or to isolate the correlation resulting from one factor while controlling for another. If W represents cluster membership or another factor that it is desirable to control, we can stratify the data based on the value of W, then calculate a correlation coefficient within each stratum. The stratum level estimates can then be combined to estimate the overall correlation while controlling for W variance. Variations of the correlation coefficient can be calculated for different purposes. Here are some examples. Adjusted correlation coefficient. The sample correlation coefficient R is not an unbiased estimate of ρ. For data that follows a bivariate normal distribution, the expectation E for the sample correlation coefficient R of a normal bivariate is therefore R is a biased estimator of the unique minimum variance. Unbiased estimator RADJ is given by, where, A defined as above, is the Gaussian hypergeometric function. An approximately unbiased estimator RADJ can be obtained by truncating E, R, and solving this truncated equation. The solution to equation is wherein are defined as above. RADJ is a suboptimal estimator. RADJ can also be obtained by maximizing log. RADJ has minimum variance for large values of n. RADJ has a bias of order 1. Another proposed adjusted correlation coefficient is, note that RADJ are for large values of n. Weighted correlation coefficients suppose observations to be correlated have differing degrees of importance that can be expressed with a weight vector W. To calculate the correlation between vectors x and y with the weight vector W, weighted mean, weighted covariance, weighted correlation, reflective correlation coefficient. The reflective correlation is a variant of Pearson's correlation in which the data are not centered around their mean values. The population reflective correlation is the reflective correlation is symmetric, but it is not invariant under translation. The sample reflective correlation is the weighted version of the sample reflective correlation is scaled correlation coefficient. Scaled correlation is a variant of Pearson's correlation in which the range of the data is restricted intentionally and in a controlled manner to reveal correlations between fast components in time series. Scaled correlation is defined as average correlation across short segments of data. Let be the number of segments that can fit into the total length of the signal for a given scale. The scaled correlation across the entire signals is then computed as whereas Pearson's coefficient of correlation for segment. By choosing the parameter, the range of values is reduced and the correlations on long timescale are filtered out, only the correlations on short timescales being revealed. Thus, the contributions of slow components are removed and those of fast components are retained. Pearson's distance, a distance metric for two variables x and y known as Pearson's distance, can be defined from their correlation coefficient as, considering that the Pearson correlation coefficient falls between -1, 1, the Pearson distance lies in 0, 2.